now I get, let's see, let's put this over here. So now I get d squared x is this, 2a e to the t plus a t e to the t. Minus 6 of these, so minus 6a e to the t minus 6a t e to the t plus 5 of these, 5a t e to the t has to equal negative 4 e to the t. So notice a t e to the t minus 6a t e to the t plus 5a t e to the t is 0. Why is that a good thing? Why does that have to happen?
Because there's none of them on there.
There's no t e to the t's. A would be 0, we'd be screwed. Okay, and then I get negative 4a has to equal negative 4. That's beautiful. A is 1. Yay. Is that cool? Coefficients of the e to the t. Negative 4a of these has to equal negative 4 of these. Negative 4a has to be negative 4. So a is 1. So now I'm done with the x part, which is apparently all I was asking for. Who gives a shit about y, man? X equals c1 e to the 5t plus c2 e to the t plus, where'd it go? T, what is it? T e to the t, because a is 1. Okay. Now, if you know, it was a regular final exam problem, how would you figure out what y is? Well, you can solve this for y and then just plug it in. Not a big deal. Just plug your x in. And you don't have to worry about equating your c's because you're going to have the same c's carried throughout. Okay. So believe it or not, I mean, real quick, there are rates of changes of things that depend on the amounts of two different things that are present. That is basically the idea behind this. So if you can get two different relationships between all that, then you can solve it for the two amount equations at certain times, right? That's one way to kind of look at it physically. Yeah.
Could you remember that word?
All right. Okay. So let's see. So we got this. Yeah, I think. Well, I'm gonna come Wednesday with the answer key for this copies for everybody, and then I'll probably bring a little, some kind of little worksheet or something extra. We'll see. Let's see, 10. So what's A? What's that matrix?
Negative 4, 6, negative 3, 5.
So then I want to investigate the determinant of A minus lambda I. So we are skipping a lot of idea to get to this, but this is the idea that always happens the same way. I can write this as in a matrix equation form, and then the only way to have what I need to have happen is for the determinant of this guy to be 0. And that's where I get my eigenvalues, that lead to my eigenvectors, so forth. Now, the less you've done with matrices, the more uncomfortable you are with all of what I just said. The nice thing is you can kind of skip most of the ideas. Well, you know, part of me kind of is cringing a little bit about that, but you can go straight to this. For a 2x2 matrix, you had to know determinants of matrices for this class anyway. And that's really the heart of the work you've got to really do. You have to understand matrices better to understand why this is the way it is, but the work you actually have to do is basically based on that, and then factoring a little polynomial. So what's this determinant? Right, determinant form. Yeah, AD minus BCLE. So A minus lambda I, that would be, so I take -4 minus lambda, 6, -3, 5 minus lambda, oops, determinant. Because lambda I would just be lambda 0, 0, lambda. So if I take that minus this, I get that. And so what is this determinant? Let's see. Try to work that determinant out. Yeah, exactly. So let's see. Lambda square plus 4 minus 5, so minus lambda minus 20 plus 18, so minus 2. Is that factorable?
Mm-hmm.
Yay. So lambda. Minus 2. The bigger one's got to be negative, so it comes out negative in the middle. Yeah, they're extra equals. So then your two eigenvalues are 2 and -1. Part of me just feels so bad for any of you that won't get to work much with the eigenvalues. You know, most of you probably should, because a lot of you guys are future engineers. Future engineers use the hell out of eigenvalues, if I remember correctly. So now I look at each one separately. So if I say lambda is 2, what does that A minus lambda I look like now? I get -6, 6, -3, 3. Right? It's not determined anymore. No. And this is times K1, K2 equals 0, 0. So what's got to be true then? This is almost always going to happen. This is why they're eigenvalues, because they lead to such strange yet beautifully simple matrix problems. Either way you look at it, negative K1 plus K2 equals 0, so therefore K1 has to equal K2. Right? Negative 6K1s plus 6K2s is 0, so then K1 has to equal K2. And this one says effectively the same damn thing. That will always happen. That's what eigenvalues cause to happen. They are weird little things that make weird things happen to your matrix.
Why did we get 0, 0 around the end?
Oh, because remember, some of the stuff we skipped to get to this was the idea, oops.
Oh, okay.
That guy, yeah. So really, I'm just taking what I've done here and plugging it back into this, using those special values I found here.
And
They're
that's
all
and that's always true. A minus
Yes.
lambda I
Yes.
times K always
cool
equals 0.
for the form of matrix DE that can be put in a matrix that we're looking at.
Okay.
Yeah. Notice, I mean, the problem we're working with is very basic. Do you agree with me? Yeah. But you can amp this up, obviously, because you make matrices grow as much as you want. You can make the original problem grow as much as you want. Introduce more and more and more variables. Yay! No. And then, so what about the other one? So for lambda equals 2, I get k1 equals k2. So this would be like 1, 1. Fundamentally, right? C1 times 1, 1. K1 equals K2. And for lambda equal -1, you do the same thing. So it would get, what is it, -1, so -3, 6, -3, 6. Well, that really is in your face that they're the same thing. Oh, and let me see, I don't write this.
K1 equal
Say again?
K1 equal half K, K2.
Or negative 2k2.
Positive.
Positive.
Positive 2K.
Yeah. So -3k1 equals 6k2. So if you add the 3k1 over, divide by 3, you get k1 equals 2k2. So that basically ends up being 2, 1. People always get that turn around. If k2 is 1, then k1 is 2. All right, so now what does this mean in terms of the answer then? Where do I want to put this? All right, let me take this away. So we started off with let me see, remember. Yeah. This, because then if you take x prime, you get k lambda e to the lambda t. Yeah, cool, I like it. And then the general form of the problem was this. So then you get k lambda e to the lambda t equals a k e to the lambda t, which eventually leads to all the stuff. I think. Am I missing something? No. I like it. Beautiful. Yeah, beautiful. Okay. Just to remind you, this is the form of the answer. Where this is big X, right? This is not just X. This has X and Y in it. And X prime has got X prime and Y prime in it. So the answer then would be, where are we at? C1, 1, 1, gather. E to the, now what did 1, 1 go with?
K1 K2.
Lambda equals 2. E to the 2t plus C2, 2, 1, e to the negative 2. Or if you wanted to, this would be C1 e to the 2t plus 2c2 e to the negative t. And y would be C1 e to the 2t plus C2 e to the negative t. You can break that up in the xy. This is x1. Yeah.
Is the C1 just because it's like K1, K1, and then it's just, instead of calling K, you call it C?
Yeah, just to make it match. If I did this 4, 9, I wouldn't have k's. The k is sort of for the matrix stuff.
Yeah,
I can't remember. I think the book brings it back to C's too.
Isn't it supposed to be, I believe it's like a placeholder that has to do with the, when you have the matrix for the 0 and lambda?
Well,
That's what it is, isn't it?
this step
Shift.
here, I took out, I could make this K1, K1, to be honest.
Yeah, but I thought it was used to shift your diet.
No, it's just a multiple. I really took a K1 out to find what the real vector was, but it's still a constant multiple of that thing. Yes. Okay. Da-da-da. I guess the Laplacians, you're like, I got that stuff. Hopefully. Yeah. Then we have Wednesday too. This is kind of nice.
Yeah.
This is beautiful. We did a lot tonight. So between now and Wednesday, just really figure out what it is you want to focus on. Because if nobody's asking a question, the floor is yours. It's crazy. I'm going to try to bring something too, just in case there's not a ton of questions. We have something else to look at. And I'll bring the answer key for this practice final. Cool.
Do you have any questions built into the floor, or should we ask you that at your office hours?
Oh,